Good morning. We shall begin the discussion on subject signal and system. So I start with the meaning of those two words on the or mentioned on the subject, mentioned in the title of the subject, that is signal and system. So what is a signal? Uh, when we say that we are receiving some kind of a signal, we mean that we are receiving some kind of an information. This information can be of many types. This information can be a message signal which we receive on the mobile phones, like in the form of an SMS, or when we open an internet, when we browse through the web pages, we consume some kind of an information, some kind of an digital content. That is also one kind of a signal which we are consuming. So that is also one kind of an information which we are trying to process, our mind is trying to process. So by illustrating another example, a better example, when we enter from a dark room to a proper illuminated room, we observe that something strange is happening. We observe a change. We observe a change in the illumination level. So how do our brain process this information? So we can consider our brain as a digital signal processor or a DSP. So how do we our brain sees this change in the illumination level? It sees this as the form of a signal. It sees it tries to quantify or measure the change. How much is the change in the illumination level? That change is which is being observed in the physical quantity is actually quantified as a signal. So mathematically we can represent this signal as a function of one or more independent variables which carries the information. Here I have mentioned one of the mathematical function carrying information or carrying the which is represented as a signal xt with the time as an independent variable, which is xt equals to e to the power of at. So the next question is that can time is only the independent variable for a signal? The answer is no. Time is not always an independent variable, because when we consider the variation of a physical quantities such as air pressure, temperature or wind speed, so these quantities vary with altitude of the air column or with the direction of the wind speed in the xyz coordinates of the space. So here the independent variable is the altitude or the position, xyz position in the space. So this kind of a signal is used to understand the study the aspects of the meteorological investigations. Now coming to the classification of signals, as I have already described, that the signal can represent any kind of an information. So is signal message signal, information signal, or the SMS, internet data, these are the types of a signal? Or no, the signals are basically classified into more broader terms, which is mentioned as a continuous and a discrete time signal. So coming to the basic classification, continuous signal is also called as an analogous signal. Analog in the sense that it is described at every instant of a time. For every real value of a time, we have the value of the information x of t. So it is a continuous in time. It is continuous in a time domain, because for every instant we get for every instant in time we get some kind of an information x of t. And now when we sample the continuous time signal at a discrete levels of a time, then what we obtain is called as a discrete time signal. So sampling is one phase to convert the continuous time signal to a discrete time signal. And further, when we quantize the discrete time signal, we obtain a digital signal which we use for a digital signal processor. So this is the one classification of a signal in the form of a continuous and a discrete time signal, which we are not going to study further. Here I am basically will describe about periodic and aperiodic signal. This is the classification of a signal which we are going to study. So what is a periodic signal? So Periodic signal, it means that something which is repetitive in nature. So mathematically it should satisfy the equation x of t plus time period capital T equals to x of t, meaning it means that its values represent after every time period t seconds, because values, suppose I have a I measure at if I strike at a certain instant t1 of a signal, and I try to measure the values between an instant t1 and its time period t1 plus t. So those values between t1 and t1 plus t, this is going to repeat after the interval of t. So this information, or this amount of an information between in the instant t and t plus t can be wrapped into a one signal, can be wrapped into a circle. So what I am trying to convey is that using the one lap of a one lap of a one time period of a periodic signal, we can envelop that information into wrap the information into a circle. This is elaborated in the figure, where I have wrapped a triangular function into a shape of a or into the shape of a circle. Now when it is wrapped as a circular function, then by striking this triangular signal with a different radii of circles, we will obtain the different points on the we will obtain the different points in the x and y, in the xt and yt domain. So these points, these points on the triangular waves at different points, we can create our own mathematical formulas of getting those cut points. Suppose circle of radius r by 2 cut the triangular wave at a point x1t, x2, y1t, then another at x2t, y2t, another at x3t, y3t, another at x4t, y4t. So we get those points for a one specific circle cutting that triangular wave. Now consider a radius of 2r, the circle with a radius 2r. It will cut the triangular wave is to get some another points in the space of xt and yt. So suppose when we get all those points and try to reconstruct back the triangular pulse, the triangular wave, we obtain the we try to reconstruct the triangular function from the sampling of with the help of circles. So this is one kind of a sampling phenomena which we have observed. Now we have a circle of radius unity, and from our studies at a primary level, we know that the equation of a circle is represented as x square plus y square equals to, which is the radius of the circle, which is unity 1. Now considering the x coordinate of the system, the what can be a function of x and y which will try to get me the value unity. So if I take x as a cos t and y as a sin t, then squaring the both term will get us unity. So x can be represented as the cos t and y can be represented as a sin t to define a circle. Now suppose, as I have already discussed, that any periodic function or any periodic signal can be wrapped into a circular information or into a circular shape. So once a periodic function is wrapped into a circle and we try to find the components of the wrapped information, we get in the form of a sine t and cos t. Here we can see or observe that the sine t and cos t component of the signal are 90 degree apart, which is defined as a which is the simplest form of orthogonality. When we try to take a component which is mutually perpendicular, this is one kind of orthogonal, which is one kind of the orthogonality which we are defining. So this here is one of the note which I would like to mention, that this explain why Fourier coefficients are complex, because the we can observe that the y component of the signal is displaced physically 90 degree to the cos of t. So sin t is displaced in the space by 90 degree. So that is one of the reason why we get Fourier coefficients as a complex number when we describe the periodic signal in terms of a Fourier series. And another note which I like to mention here is that when defining any other function, can we define any other basis function for xt and yt which describes the equation of a circle? The answer is yes, we can have another basis functions of xt and yt. We can have xt equals to 1 minus t square by 1 plus t square, and yt equals to 2t by 1 plus t square. And when we square it and add it, we get unity as as an equation which is describing a circle. So can xt and yt be considered as a basis function instead of sin t and cos t, which is the general form in which any periodic signal is represented in the components of a Fourier series? The answer is no. This can't be a basis function, because this signal, this xt and yt are itself in aperiodic in nature. They only form a circle, they complete the circle, but they itself is aperiodic, so they can't form the basis for the Fourier series. But in high performance computing and embedded control system like a small microcontroller, calculating a sine function and a cosine function is expensive in terms of a CPU cycles. So how do we calculate? Suppose I want to find sine of 45. We give input to the microcontroller to calculate sine of 45 degree. So will it able to, is there any lookup table which my microcontroller looks into to calculate the value of sine 45? Oh, the answer is no. It tries to use the Taylor series expansion of sine theta and cos theta to calculate the value of a sine 45 degree, because my microcontroller or my microprocessor only has some suitable amount of operations which it can perform. Like it has an ALU, arithmetic and logic unit, which can perform additional and a logical operation. It can perform addition, subtraction, multiplication, but it cannot calculate the sign of a value. So we try to approximate this sinusoidal function into some other functions which we can add it to get us, or which we can multiply or perform the combination of arithmetic operation to obtain a sinusoidal function. That is one form of a Taylor series expansion. Or what we can do other than this is that we can parameterize the sinusoidal function and the cosine function in the form of xt and yt, which I have described as a circular equation. And then we can use this t, the variation of t can be in the form of t plus del t. So at different instants of t plus del t, we will obtain the sine and cosine value for different degrees. So this is one of the optimization hack which we utilize to calculate the sinusoidal functions. Which bring me again to the definition of orthogonality of a signals. As I have explained that any signal can be wrapped in the circular shape. Any periodic signal can be considered wrapped in the circular information, and we have components of cos t and sin t which is physically displaced or which are orthogonal to each other. Now Is that only the definition of orthogonality for a signals, or we can define the orthogonality in more better way? So the answer is that we can utilize the same concept of a orthogonal signal, but here we will consider the projections of one signal onto the another signal. So what do we mean by a projection? Suppose we have a two vector in a vector space. The projection of one vector on another vector, if they are mutually orthogonal or mutually perpendicular, the projection will be zero. So that is the concept which we utilize to define the definition for the orthogonality of a signals. So here I have treated A1 as a phasor which is rotating at an angular speed omega, and A2 which is rotating at an angular speed 2 omega. By treating A1 as a stationary, A2 will be rotating at a speed at the relative speed of omega, and at any given instant the projection of A2 onto A1 is calculated to measure the amount of interaction between, or the alignment between, A2 and A1. And when we integrate or sum this projection of A2 vector over its one lap of an interval, we will come to know that the integration of the summation over the one complete interval of its time period is 0. So this sinusoidal signal with a frequency omega and 2 omega are mutually orthogonal, and this is one of the definition of orthogonality of the signals. So which is mathematically represented as the inner product formula, which is integrated from time period A to B, and with the product of the two signals which result in the zero value, which inner product is resulted in a zero value, and we can confirm that both the signals are orthogonal, both the signals are periodic. So just as we can establish a traditional vector space, can we construct a signal space? Here the answer is yes. We can construct a signal space using sine and cosine function as our basis, and these functions are inherently orthogonal to one another, meaning the x movement has zero effect on the y movement. I am exceeding the time, so I will try to wrap up this discussion by the foundational concept of a Fourier series. So I have developed this much of a foundation to introduce the concept of a Fourier series. So Fourier series basically means we can represent any periodic signal as a linear combination of orthogonal basis functions which we have described. So here is one of the images or one of the animation which I have taken from the Wikipedia to show that any periodic function or any by appropriately adjusting the amplitude of the periodic function, the coefficients, the amplitude of different frequency components, we can obtain the periodic, or we can synthesize the periodic functions, any shape of the periodic functions. Thank you.